Hello. In terms of magnetism, sources of magnetic field, it's going to be a little while for the clicker questions.
Okay.
And so when we talked about the electric field, we had the electrostatic rectangle. We had force, U, V, P, and remember everything at every point was for a point charge. And so the electric field of a point charge was given this way. And the way we went from a little bit of point charge to a lot of point charge was first we took it into a differential.
Right.
Where we had dE is equal to k dq over r squared r hat. And then we did an integral with that. Board work is going to be pretty interesting today. And so that's the method that we followed. We're going to be doing that exact same process today, except with magnetic fields. And was that the point that you were going to point out? Okay, cool. Yeah, please, if you find any mistakes, let me know. Otherwise, they're just going to be like, burnt into the video. All right, so the Biot-Savart Law, as you can see from that well-placed screen over there, we do have the cross product in there. So we have, it is a vector, and it's mu naught over 4 pi q v vector cross r hat over r squared. So it has a similar form to the electric field due to a point charge. Now you have a moving charge. Okay, oh, and I even have this one kind of animated. So this is the permeability of free space. And so what does free space mean?
Like a vacuum.
Vacuum, excellent. And notice it's similar to that you've got that 1 over 4 pi aspect, and it turns out that mu naught and epsilon naught are related to each other and the speed of light. So we'll get to that in a couple more weeks. So you have, remember that the charge has to be moving, and then now the r hat, it points from where from the charge to where you're calculating the magnetic field. So if I have this charge and it's moving in the positive x direction, and I want to know what is the magnetic field, this would be the r hat direction.
Okay.
And it's going to get pretty funky because we're going to have to work in 3D writing things on a 2D space. Okay. So mu naught, the permeability of free space, it's just 4 pi times 10 to the negative 7 Tm over A. And so if we got the speed here, and I'm just drawing the on the slide, this figure, and this is slide number 4. And also this is lecture 21. Just for the people that are watching the video. Okay. And so here's my positive charge. Now, oops, I'm going to move that B to here. Now what happens is that you have to do the cross product, and so the magnetic field is actually perpendicular to the plane created by V and r hat. Okay. And so we've got V cross r hat gives me B. And so V is out of the page, or the board in this case. We also have this inverse square dependence. Oh, I think that's actually the next little thing. Okay, and that's the distance between the point charge, that moving point charge, and that position. Remember, this thing's moving, so it's r is going to change. So what we're going to do is really going to look for symmetric charge movement and those kinds of configurations, similar to what we did with the electric field for a rod of length L, an infinitely long rod, a cylinder of charge, or a sphere of charge. We're going to be doing those same kind of actions. So, any questions so far?
So that the drawing you just drew, that's just like because this thing is moving, so that's just like at some random point in time when it's like it looks like it's still.
Yeah, it's a snapshot. at t is equal to 0.
Okay.
Yeah, that's an important thing to point out. Yeah, it's a snapshot view. And so a lot of times when you're asked, like, what is the magnetic field at this, for this situation, then you're really doing the right-hand rule. Okay, so let's see. So V cross R comes out of the board, and so the correct answer is D. So this is this example problem talks about, and this is on slide 7, B field of a moving point charge. If an electron moves along the z-axis with a speed of 2.0 times 10 to the 7 meters per second, as it passes the origin, what is the strength and direction of the magnetic field at this position? So we have X is out of the board, Y is to the right, Z is up, and we have our particle, it's an electron, so Q is equal to negative E, and it's moving up with a velocity of 2.0 times 10 to the 7 meters per second. And it wants to know what is the strength and direction of the magnetic field at that place where the location, oops, sorry, I have it drawn incorrectly from what the board says. Here we go. And that position is 100 centimeters. How's it going?
Good.
Okay, you're just writing the stuff down? Okay.
Yeah, I'm trying to
So
calculate
we've got QV cross R hat over R squared. And for this problem, what is R hat?
It's the length of, it's the length to that point from the,
The R hat part.
oh, are you saying like the hat? That's
Yeah, what's the R hat?
the unit vector?
And for this particular problem, R hat is equal to?
Let's see, 1.
That's the length of the unit vector. Which way does it point?
Oh, in the direction of the x.
Yes. So R hat is equal to I hat.
Right.
Because, let's see, yep, right there. And so we know that V, the velocity is perpendicular to R because this is in the z direction. And so with a simple case like this, we can automatically just go A cross B is equal to A, B, sine angle between them. And it's just the sine of 90 degrees. And so whenever you have a perpendicular arrangement, you're going to get the strongest magnetic field right there. So let's just do that. So moving up here, we've got V is equal to mu naught over 4 pi. We have negative E as the charge. We have V, and it's, up there. And we have just 1, because it's a unit vector. And then what about R squared, what goes in the denominator?
Just the length of r, which is 1 centimeter.
So 1 centimeter, it's 0.01 meters, and that's squared. So this gives me the magnitude. Okay, what's the direction of the magnetic field?
Magnetic fields in the direction of r hat.
So remember, we've got this cross product.
Oh.
Yeah, so we have to do that right-hand rule again.
So it's going to be in the y direction.
But V, and then X is out of the board. V cross X gives me positive Y. So that's positive J hat. One of the things I want to point out, though, look at this negative sign.
Oh.
Because it's an electron, this negative sign actually carries over to the direction. And so what we have is mu naught over 4 pi E times BZ over 0.01 meters quantity squared times negative j hat. A proton would move in the positive y direction, but here we have an electron, so it moves in the negative y direction. So the sign of the charge actually plays a role in the direction. Very similar to the force on a charge in an external electric field. Electrons experience a force in the opposite direction as the electric field. Okay. So we have 4 pi times 10 to the negative 7 Tm over A over 4 pi. And that's always nice and convenient here. We have 1.60 times 10 to the negative 19 coulombs times, and it's actually meters per second, that's good, 2.0 times 10 to the 7 meters per second over 0.01 meters quantity squared. And now I need you to, and it's in the negative j hat direction. Four pi's cancel. Okay, 1.6 times 2 is 32. Okay, right?
Yeah.
3.2 times 10. Negative 2, negative 4, positive 4. Negative 15. These cancel. Do you get negative 15?
3.2.
I did math in here.
Wow.
All right. And what are the units of magnetic field? There's a car named after it.
Tesla.
Yes.
Tesla.
Yeah. So 3.2 times 10 to the negative 15 Tesla. Much smaller than the electric fields that we were used to dealing with. And part of that is this mu naught over 4 pi. Remember, K is about equal to 9 times 10 to the, what is it?
9.
Okay, 9. Okay. So we're multiplying, for calculating the electric field, something times almost 10 to the 10. Here, for the magnetic field, in terms of this, you're talking about multiplying it by 10 to the negative 7. Magnetic fields are typically very, very weak compared to electric fields. And that's also going to come about when we start talking about electromagnetic waves. So just to give you kind of like a little taster and teaser for future, we've talked about electrostatics and electricity. Now we're coming over here and we're talking about magnetic fields. And then what we're going to do is see that electricity and magnetism are two sides of the same coin. And so we're going to bring them together and realize that we're talking about electromagnetism. Just what aspect are we looking at? What do you think?
Interesting.
So everything's still okay so far? Okay. Alrighty, another clicker question. Polling is open. And while you're looking at that, I'm going to erase the board.
My battery's here.
Alright, so a lot of times we don't really care about the magnetic field that's created by a single point charge. What we care about is that magnetic field due to current carrying wires. And we already talked about how the right-hand rule allows you to, in this case, and this is slide 11, you put your thumb in the direction of the wire, your fingers curl in the direction of the magnetic field. Okay. So what we're going to do is now this transition from going to the Biot-Savart Law, which I still have written up on the board, take that to a differential form, and then figure out the magnetic field due to a long straight wire. First thing I'm going to do is remember that how do we define, just generally speaking, how do we define current?
A moving charge. Oh.
Okay,
right.
so if an amp is equal to coulomb per second, that's the units of current, then mathematically, how do I define current? Not using Ohm's law, but...
So, charge over time?
Yep. dq dt. Okay. So, let's see. if I have this point charge here, okay, and it's moving, then I have Q times V. But that is equal to Q times dx dt. Now what I'm going to do is back off a little bit, and I'm going to talk about, well, how much charge is moving over what distance in what amount of time? And then I'm going to rearrange that as dq over, sorry, delta q over delta t times delta x. And now what I've got is the current times delta s. Now, here, there we go. Oops, x. So now what I can do is talk about the Biot-Savart Law from the perspective of a point charge and put it in perspective of a current. Okay. And so that becomes mu naught over 4 pi times the current times delta, and I'm going to go from x, which is very specific to a coordinate system, to just some distance, delta s, cross r hat, there it is, over r squared. Okay. So, remember r squared is just distance from the current to where the B field, you want to know like what the direction and the strength of the B field is at a particular point. So S is just some distance, some bit of charge. So you'll often see the magnetic field this way. Okay. So even though the picture on the slide is vertical with the wire, here I'm going to do a horizontal, because otherwise if I flip things on my notes, I'm going to get it all backed up or backwards. So make this a little bit bigger. Here I have my wire. Okay. Just to make it so you can still see the axes. And what I have is I have a current that's traveling to the right. So that's the notation in the back of that arrow. Current is traveling from left to right. My vertical axis is the y-axis. And here, I have that little bit of length. And here, I have a little bit of charge. Okay. And then let's say I want to know what my magnetic field is at that point, and that point is a distance d away from the center of the wire. And there's my angle. Okay. So, do you see how I'm going to start taking components and I'm going to use trig functions similar to how we did it for the electric field? Yeah. Okay, good. So, I can use the right-hand rule to give me the direction. So what I'm going to do now is just focus on the magnitude of the magnetic field. So what I have is mu naught over 4 pi times I delta x times 1. Remember, that's my r hat, times the sine of theta divided by, now here, I've got this distance between that little segment of current to here. And so that's r squared is equal to, come on, Carrie, delta x squared plus d squared. That's not delta x squared.
Wait, that x squared.
Yeah, it's this length. That length is right there. X squared plus d squared, all of that stays squared. Okay. Now I can also talk about the sine of that angle and how am I going to represent the sine?
In terms of the triangle you made,
So the sine of that angle is equal to
d over x squared plus d squared.
Opposite over hypotenuse.
Root, not
Yes.
yes.
So we're going to end up with the 3/2 of the that term at the bottom. Okay. So substituting all of that in, what I get is the magnetic field is equal to mu naught over 4 pi I delta x times d. This d is the distance from the wire to that position over x squared plus d squared to the 3/2. This is 2/2 plus 1/2 over here. Okay. Alrighty. Now, what I'm going to do is I'm going to say, well, this is just, that's just a little bit of magnetic field. And I want to find all of the magnetic field. So the delta V and the delta X go to dx and dV. So I've got dV is equal to mu naught over 4 pi. Now I'm going to pull out the I and the D. I've got dx over x squared plus d squared quantity to the 3/2. What I'm going to do is take the integral of both sides. And this will give me the magnitude of my magnetic field. All right, so if it's a long straight wire, what are the limits?
0 to L.
Long straight wire.
Oh.
It's introductory physics long.
Oh, so they infinity to infinity?
That's right. Long straight wire, just kind of like very smooth surface, is frictionless in introductory physics. Very like long straight wire. So we've got negative infinity, positive infinity. Okay. When you do that, what you end up getting is that the magnetic field for a long wire, and if you want, from this position, or this distance d away from it, you get u naught times the current over 2 pi d. Now, a lot of here we use d, the distance, but basically r is just the distance away. Fingers curl in the direction of the magnetic field. So we have this closed loop, and here the current flows from left to right. So the magnetic field is out of the board above the wire, and it's into the board below the wire, pointing down in front, up, and back. Okay. So if I have this wire, where the current is going from left to right, and we've got that the magnetic field is equal to mu naught I over 2 pi, and I'll do r, distance from wire. I want you to sketch what the magnetic field looks like. So just in this region, above and below. And I want you to draw like at least 3 rows of dots or crosses. Kind of visualize the electric field. And this is also a very long wire. So, above the wire, the field is coming out. Below the wire, field's coming in. what is the field strength here? So if I have this distance r, what about another r away? What is the field strength twice as far away compared to here? Half as strong because of that 1 over r. So when we draw electric fields, the spacing, now the magnetic field's not going to get weaker as we go from left to right because we have this very long wire. We've got these loops all the way around. But as we go further away from it, it's going to get weaker and weaker and weaker. And so the way we visualize that is taking these rows and spacing them further and further apart. So you'll see spacing of the magnetic fields with this notation in your book. And when you're drawing it and visualizing it and stuff like that, just be aware of that, because what we're going to, the next topic we're going to is electromagnetic induction. We're looking at how does the magnetic field or the electric field change, how does that flux change in time as a function of time. So if it's getting weaker or stronger. And so if I'm here and I'm moving here, then the magnetic field gets weaker. So it can be very useful to have that kind of visualization right there to remind you. So I have this example problem, but I would like to move on. Besides, here's the solution to that example problem. So that's the example problem on slide 12. And also, because I'm videotaping it, I'm trying to provide some context for the people that are just listening because they can't see both. Okay. Now we discussed the magnetic field of a current loop. Wow, that was only yesterday in class, right? Mm-hmm. So in terms of when you're curling your fingers in the direction of the current for a current loop, fingers curl in the direction of the current, your thumb points in the direction of the magnetic field inside that loop. And notice how on the slide they've drawn it as though it's a magnet. Your thumb points in the direction of the North Pole. And I think you even drew that on the whiteboard. Mm-hmm. So if we don't have a magnetic material, we can create a magnet using current. It's an electromagnet. And I think you all are going to be building one. You're going to be building one for the radio project, for your circuits project. So you're going to get to wind it a lot. It's going to take a while. So what we can also do is take this same approach for the long line, and we can talk about the magnetic field on the axis of a current loop and calculate the function for that. So with magnetic fields, in this class we're going to stick with very, very symmetric situations. Some part way from a very long wire, and it can be, or there's a wire, and if you're halfway in between but you're pretty close to a wire, it looks like an infinitely long wire, similar to a disk of charge. If we're really, really close to it, then it becomes infinitely large from our perspective. So we're going to do this. From the Biot-Savart Law, U is equal to mu naught over 4 pi QV cross r hat over r squared. And we've already seen how we can take that into a differential element with a little bit of current, a little line of current. So mu naught over 4 pi I times dl cross r hat over r squared. So let me draw this. Let's see if I can draw it fairly well. No guarantees. So I'm going to make the z-axis along the center and take the y-axis up and the x-axis here. So it's hard to draw 3D things on a 2D plane. So this loop, this current loop, is in the x-y plane. Okay. Perpendicular to board. And the way that they've got it drawn is if we're looking from the positive z-axis down towards it, and this loop is right here, the current is actually out of the board at the top into the board at the bottom. So the current is flowing this way. So the current, there's a little bit of current from dl. Okay. And so what I want to do is, what is the magnetic field at some point P right here? Do I have that same notation? Kinda. All right. Capital R is the radius of my loop. Now, from this little bit of this differential element of current L, see if I can draw my triangle a little bit better. Okay. Let me use another color because I can. So we've got the triangle is actually in the YZ plane. Oops. So that's my angle. R hat points from our little source of current towards the point that I'm looking for. So this is actually R hat. Okay. So I've got, now we get to do the right hand for the fun time. I've got current coming out here. I've got R pointing here. Okay, so now I've got a little bit of current across R hat. Current here, there. So it's actually, it's from this, so I cross R, it's kind of cockeyed. What I have is dB, that little differential element of magnetic field is in that direction. But we have this symmetric system, because it's a loop. So if I take a little bit of differential current at the very bottom, what's going to happen? What is going to happen? I have a little bit of differential current here, and I'm looking at the magnetic field at this point. What would I anticipate the net magnetic field to point in? Which direction?
In the Z direction.
In the Z direction. And notice how that also aligns with our right hand rule. Okay. So what I want is, I want that Z component. The Z component survives. Alrighty, so now when we talk about these cross products, I have an angle here, but we need to be careful about how we talk about the different angles. Okay. So I have B is equal to mu naught over 4 pi I dl cross r hat over r squared is equal to mu naught over 4 pi I dl sine of the angle between I dl and r. Okay, over, oops, that's at the center. That's the wrong page. That's what I want. Okay, over r squared. Now, this IDL points out of the board. this r hat points down. It is 90. This b is in the yz plane. This little bit of element is in the yx plane. Those planes are perpendicular to each other. Okay. The plane of the r hat vector, the plane of the ideal vector, 90 degrees. So that's just the magnitude of that little bit of dV. Oops. Okay. There we go. Now I'm writing stuff. So that dV is equal to mu naught over 4 pi dl over r squared. And the part that I care about I want the z component. I want the part of the magnetic field that lies along the z-axis. So, for the z component, let me talk about, let me call this angle component. Okay, this angle is angle vectors, or angle cross product. So if I just want the z component along this axis, notice that these are perpendicular. Okay. Then how do I just pull out the z component? Okay, now I gotta figure out the angles. Okay. Did I do that wrong? So this is a straight line. If this is the angle component, that is the angle component. If that is, if that's a right triangle, okay, then this angle is theta component. And so this would be 90 minus theta component. Okay. So it ends up being a relative triangle thing. Okay. All right, now, what's actually the z component?
The sine.
It's the sine. Okay. Yeah. And of course, what's the hypotenuse of this large triangle?
Root r squared plus c squared.
Because this is r, and this is z. Yep, it's capital R. So what we end up having is dBz is equal to mu naught over 4 pi times I dl, and now I've got capital R, in terms of, because I'm using the sine of this one, capital R over, I've got r squared plus z squared. I've got it squared here, plus the hypotenuse from the sine. All of that together gives me the 3/2. And then what I need to do is integrate. When I integrate dl, I go all the way around. Oops. So it's this loop integral, and here I'm talking about a little bit of line. So if I go all the way around the circle, what's that little bit?
2 pi r.
2 pi r, so circumference. If I have one little segment of the circle, and I go all the way around the circle, I get the entire circumference. And so then I just get 2 pi r. Okay. So the magnetic field, let me just put it all out there. So mu naught over 4 pi times I times 2 pi r. Yep, and that's 2 pi capital R carried. And then I have r, still from the integral. And then I have times r squared plus z squared, and that's to the 3/2. Because the dl doesn't matter. The capital R and the z are constants for this integral. Yeah.
Since that's the magnitude of the magnetic field, do we just drop that? Because I know for when you integrate it, you had it for d sub z for because it's you have it as a z component.
Okay. So yeah. So here it's on the axis.
Okay.
Yeah. So then the 2 pi in the numerator cancels out the pi, and half of that 4 pi in the denominator. So now we're talking about the magnetic field on the axis of a loop. And that is equal to u times I times capital R squared over 2 quantity capital R squared plus c squared to the 3/2. It is a vector. How do we find our direction?
Right hand.
Right hand rule. RHR, right hand rule. There we go. And if you want to find the magnetic field at the very center of that loop, the z goes to 0. So the closer I am, the stronger the magnetic field is. And so when z goes to 0, it simplifies to that. U naught times the current over 2 times the radius. The larger the radius, the weaker the magnetic field at the center. And that hopefully is kind of intuitive. The more current you have going through it, the stronger the magnetic field. Okay, remember we have a principle of superposition. We had the disk magnets in class, and we put more of them together, we made a stronger magnet. The exact same thing happens with loops. More loops, more current. And so if I have n loops, then I have made my magnetic field n times stronger. And here what you're doing is, even though that figure, this is on slide 16. So what you're doing here is you're assuming a very thin coil. You're not talking about a slinky. A slinky is a solenoid, and we're going to do that on Friday, which is only tomorrow. So here we're talking about a very, very thin wire. So these loops are really right on top of each other. We actually got through all the slides. Okay. So what we're going to do is, now that we've dealt with all of that interesting calculus, what I'm going to do is we're going to play with Ampere's law tomorrow and see how much easier it can be. Kind of like how Gauss's law, you could calculate the electric field for symmetric charge distributions by pulling it out of the integral. We're going to do the same thing, and it's called Ampere's law. It's one of Maxwell's 4 equations.